Hello everyone. I hope all you are doing very good. Today in this topic we will try to cover equation of motion for a free oscillation, natural frequency of oscillation. After that, very important topic, that is damped oscillation. There is a 8 marks derivation which may come in the VTU semester exam, which is damped oscillation or theory of damped oscillation. So before we begin with damped oscillation, I request you to subscribe to my channel so that it will help to me, it will help to my channel so that I can get motivation to create a content like this so I can improve it in the future. Thank you. With this, we'll roll the intro. Before we are going to see what is free oscillation and all, let me tell you what is the main difference between oscillation and vibration. Usually, if we define oscillation means to and fro motion, with that we call it as oscillation. But in the case of vibration also we can see the to and fro motion only. But the thing is, the only main difference is with frequency. In the case of oscillation we can see less frequency. In the case of vibration we can see high frequency. That means there is a difference between oscillation and vibration with respect to frequency. Let's see vibration with the help of example. A guitarist playing a guitar. So in that video you can clearly see what is vibration. The vibration means nothing but oscillation only, but the only thing is it has a high frequency. This is what we call it as free vibration or free oscillation. Let's see what is the definition for free vibration. Before that, we must know what is natural frequency. The frequency with which a body vibrates freely at its own is called a natural frequency. Then let's start with free vibration. Free vibration can be defined as the vibration in which the body vibrates with its own natural frequency when it left free. That means whenever a body starts its oscillation, the frequency of that oscillation will not going to be diminished after some time. That is what we call it as a free oscillation, or we are not applying any kind of force which is going to be make it to stop that oscillation. So this type of oscillation we call it as free oscillation. For example, if we take a pendulum and the pendulum is going to be having a free oscillation, in that case we can see the frequency for that pendulum is nu is equals to 1 by 2 pi into under root g divided by L, where g is the acceleration due to gravity, L is the length of the wire. This is the example for free oscillation. Let us see some example for free oscillation. So for that we can see a simple pendulum in a vacuum, a vibration executed tuning fork in a vacuum. These are the some example we can see when we are studying about free oscillation. Why we use vacuum? Because vacuum will give any environment where we don't have any resistance for an oscillation. So due to that reason, the vibration body will not going to lose its frequency. For that we need a vacuum. As per VTU syllabus, he will not going to ask you the derivation for free oscillation. So we can directly write the equation for free oscillation is d square x by dt square plus k by m into y, that is equals to 0. This is an equation for free oscillation. Derivation part is not mentioned in your syllabus, but we have to define it. It may come for 2 marks in as per VTU syllabus. In this equation, d square x by dt square plus k by m into y equals to 0, where m is the mass, k is the force constant, y is the displacement at any instant time t of oscillating body. This is the equation for free oscillation. Sometimes he may ask you to define a natural frequency. In that case, you have to write the definition for natural frequency is with which the pendulum oscillates freely on its own where no external resistive force acts on it. That type of oscillation or that type of frequency we call it as natural frequency. So from this concept we can expect only one thing, that is a definition with equation. So it may be asked for 2 marks question in a semester exam. In the next concept we are going to see damped oscillation. In previous concept we see the definition for free oscillation. That means we are not going to apply any kind of force which is going to make it to stop that oscillation. That type of oscillation we call it as free oscillation. In the case of damped oscillation, if any body oscillating for a while, after some time, if the amplitude or the frequency of that oscillation goes on decreasing, in that case or that kind of oscillation we may say damped oscillation. So this is the major difference between free oscillation and damped oscillation. Example for damped oscillation is simple pendulum in the air. In the previous topic we used to see that the simple pendulum is in vacuum, but in the damped oscillation case the simple pendulum is in the air or tuning fork in the air. So these are some example for damped oscillation. Let's see the theory for damped oscillation. Before that, let us see this video. In this video, you can clearly observe the potential energy, kinetic energy and mechanical energy. So the simple pendulum is continuously oscillating with some force or some frequency. Let's see what happened when we kept in the air. So slowly the frequency of oscillation goes on decreasing like this, as we can see in this video. After some time, as you can see in this video, the oscillation going to be stopped, or oscillation of frequency of that oscillation is going to be diminished. This is what we call it as damped oscillation. Let's start the derivation part. Consider a body of mass executing vibration in a resistive medium. The resistive force acting on a body due to medium, that equals to minus r dx by dt, where r is the damping constant, dx by dt is the velocity of the body. So at the same time there is a restoring force which is acting on a body. That is what we are going to take it as minus k into x. K is the force constant, x is the displacement. In the case of damped oscillation, we can see two forces acting on a single body. One is resistive force and another one is restoring force. Take these two equations in one equation like this: minus r dx by dt minus k into x. That is equation number 1, which is nothing but the net resultant restoring force acting on a body is equals to minus r dx by dt minus k into x. Take it as equation number 1. In the next equation, as we already know what is the second law of Newton's, so by considering the next Newton's second law of motion, where the body experiencing a force or resultant force acting on a body is equals to m into d square x by dt square. Take it as equation number 2. Now the equation number 1 and equation number 2 we will get, where we already know the resultant force is acting on a vibrating body. So that is nothing but Newton's second law of motion. So m into d square x by dt square is equals to minus r dx by dt minus k into x. Now whatever the negative terms are there, take other side, so that m into d square x by dt square plus r into dx by dt plus k into x equals to 0. This is an equation for damped motion. So, rearranging the above equation, we can write it as d square x by dt square plus r by m into dx by dt plus k by m into x equals to 0. In the next step, we are going to consider r by m is nothing but 2b, where omega square we already know that is k by m. If we remove square, then we can write omega is equals to under root k by m. So substituting in the above equation, we can get d square x by dt square plus 2b dx by dt plus omega square into x is equals to 0. Take it as equation number 3. Now let us the solution for above equation by considering x equals to a into e raised to alpha into t. Now take this equation as 4. After this, we already know that where a, capital A and alpha are the constants. So differentiating this equation means fourth equation with respect to t for twice. So once we differentiate, we can apply in the equation number 3. So first we differentiate with respect to t, where dx by dt is equals to a into alpha into e raised to alpha t. Take it as equation number 5. Then once again differentiate d square x by dt square equals to a into alpha square into e raised to a alpha into t. Take it as equation number 6. Now we already know the value for x, the value for dx by dt, the value for d square x by dt square, which we already get in equation number 4, 5 and 6. So these three equations we are going to substitute in equation number 3. Then the equation 3 will become a, capital A alpha square e into a e raised to alpha t plus 2b capital A into alpha into e raised to alpha t plus omega square capital A into e raised to alpha t, that is equals to 0. Now just simplify the above equation by keeping the common terms outside from the bracket. That means capital A into e raised to alpha t is the common term, so keep it outside from the bracket. Then as we already know that capital A into e raised to alpha t is nothing but x, so substitute, instead of writing a into e raised to alpha t, write down x into whole bracket a square plus 2b plus omega square is equals to 0. Once we simplify the above equation, we'll get equation number 7 as we can see here. So the seventh equation is equal to 0, but it should not be. So to avoid that, we will going to consider this solution by taking the value for alpha, that alpha is equals to minus b plus or minus under root b square minus omega square. Take it as equation number 8. By using equation number 4 and 8, we can conclude a generalized solution that we can write it as like this: x equals to capital C into e raised to minus b plus under root b square minus omega square into t plus capital D into e raised to minus b minus under root b square minus omega square into t. Take it as equation number 9. So where c and d are the constant. So by using this equation, let's continue the derivation. Before that, consider time when there is a maximum displacement. That means at this time x equals to x naught, that means the displacement x equals to x naught and the time t is equals to 0. By keeping these points in mind, let us take equation number 9. Then we can write it as x naught equals to c plus d, because at the maximum displacement the t will become a 0. So whatever the connecting point with t, that will be multiplied with 0, so it will become 0. E raised to 0 is nothing but 1. So ultimately x naught equals to c plus d. Take it as equation number 10. And one more thing, At the maximum displacement, the velocities also become 0. So that means dx by dt is equals to 0. So differentiate the ninth equation by equating to 0. So then we got, so we get minus whole bracket minus b plus under root b square minus omega square into c into e raised to minus b plus under root b square minus omega square into t plus minus b minus under root b square minus omega square into capital D into e raised to minus b plus under root b square minus omega square into t is that equal to 0. So we get the t is equals to 0 into minus b plus under root b square minus omega square into c plus minus b plus under root b square minus omega square into d, that is equals to 0. So on rearranging the above term by using minus b into c plus d plus under root b square omega b square minus omega square into c minus d, then we will get minus b square into x naught plus under root b square minus omega square into c minus d. Take it as equals, that is equals to 0. So solving the above equation, ultimately we will get b x naught by under root b square minus omega square, that is equals to c minus d. Take it as equation number 11. So by adding equation number 10 and 11, we will get c is equals to x naught by 2 into 1 plus b by under root b square minus omega square. And also subtracting equation 11 from 10, we will get d is equals to x naught by 2 into 1 minus b square under root b square minus omega square. So substituting for c and d in equation number 9, we get final equation or general solution for damped oscillation, that is x equals to x naught by 2 into 1 plus b square b by under root b square minus omega square into e raised to minus b plus under root b square minus omega square into t plus x naught by 2 into 1 minus b by under root b square minus omega square into e raised to minus b plus under root b square minus omega square into t. Take it as equation number 12. This is the final equation when we derived for a damped oscillation or damped vibration. This one is the very important question we may expect in the semester exam for 10 marks. If we look at model question paper, which is previous question paper, you can see there are two question paper where in the two times also he asked what are damped oscillation and give a theory for damped oscillation and discuss the case under the damping for 10 marks. So that's why I'm telling you this is the very important question for 10 marks. You can see in other question also, once again he asked for same for 10 marks. In the next concept, the continuity of damped oscillation derivation. Sometime in a semester exam, he may ask you to explain 3 cases which comes under the damped oscillation. If he asked only the cases from the damped oscillation, that is for 6 marks, or sometimes in the derivation part also he used to ask you, like in a previous question paper as I showed in earlier slide. So let us see one by one. There are 3 cases in the damped oscillation, and how we got this diagram, let us see once again the video. Let's discuss about 3 cases for in damping. So first one is over damping or deadbeat, second one is under damping, third one is critical damping. Let's start one by one. In the case of overdamping, when the system attains equilibrium state quite slowly without making any oscillation, that type of situation we call it as overdamping. That we can denote it like this also: b square is greater than omega square. In the case of underdamping, we can see when the system is going to be decrease its oscillation or amplitude goes on decreasing with respect to time. In this case, we can see undamping, that denoted as b square is smaller than omega square. So in the next case, critical damping. So if the system attains equilibrium state or it comes to an equilibrium position quite quickly without making any oscillation, in that type of situation we call it as critical damping. This is the last case where we can see in the critical damping. After critical damping, the oscillation from a body is going to be stopped. For this we can say where b square is equals to omega square. That's it for today guys. I hope you learn all the things whatever we tried to explain in this video. If you have any queries related to this topic, please comment in a comment section. If you like this video, please like it. If you dislike this video, you can also dislike this video. If you want to help me, you can subscribe to this channel, so ultimately it will help to me, it will help to this channel to grow, so that in future we can work hard to make more content very easy and very effective to you people. Thank you. Thanks once a lot.